So, real life stuff. So this is, hopefully this is a short article here from Star Advertiser. All right, so apparently on January 14th, 2021, we had a magnitude 4 earthquake shake the southeast island of Hawaii. It just says Hawaii Island. Okay. As you can see, this is where the earthquake occurred initially. So a magnitude 4 earthquake shook the Hawaii island at 6:15 Thursday p.m. on January 14th, 2021. USGS said the quake was centered about 5 miles east northeast of Pahala and about 41 miles south southwest of Hilo at a depth of about 21 miles. The quake was too small to generate a tsunami, but the Pacific Tsunami Warning Center said some areas may have experienced shaking. The quake was located in the southwest rift zone of Kaloa volcano, according to the PTWC. Hawaiian Volcano Observatory acting scientist in charge, David Phillips, said the earthquake had no observable impact on the ongoing eruption at Kaloa's summit. This earthquake is part of the ongoing seismic swarm under the Pahala area, which started in August 2019, said in a news release Thursday night. Unlike most events associated with this swarm, this earthquake was widely felt across the island of Hawaii and as far away as Oahu. Probably butchering that. Please be aware that aftershocks are possible and may be felt. HVO continues to monitor Hawaiian volcanoes for any changes. HVO said earlier Thursday that lava continues to erupt from a vent on the northwest side of Uhala, Halamamau crater at Kaloa's summit. The seismicity remained elevated at the summit with steady tremors and a few minor earthquakes, scientists said. That's the end of the article. I did not hear about this earthquake, but got to keep you guys updated. All right, so I personally find this one interesting. This is from Silence. I bet people want me to be silent. This is from Science Daily, January 27th. Diving into Devonian Seas, which is after the Silurian and the Paleozoic, ancient marine faunas unlock secrets of warming ocean. So members of Syracuse University's College of Arts and Sciences are shining new light on an enduring mystery, one that is millions of years in the making. A team of paleontologists led by Professor Catherine Newton has increased scientists' understanding of whether Devonian marine faunas, whose fossils are lodged in a unit of bedrock in central New York known as the Hamilton Group, were stable for millions of years before succumbing to waves of extinctions. The drawing on 15 years of quantitative analysis with fellow Professor Jim Brower, who died in 2018, rest in peace, Newton was continuing to probe the structure of these ancient fossil communities among the most renowned on Earth. The group's findings, reported by the GSA, provided critical new evidence for the unusual long-term stability of these Devonian period communities. Such persistence is a long-standing scientific enigma. She and her colleagues tested the hypothesis that these ancient communities displayed coordinated stasis, a theory that attempts to explain the emergence and disappearance of species across geologic time. I remember learning in historical geology that there was a major extinction event at the end of the Devonian, which typically that's what ends a geologic period anyways, is a extinction event. Been 23 extinction events, I believe, in Earth's history. Mass extinction events. Newton and Brower, along with their student Willis Newman, found that Devonian marine communities vary more in species composition that the theory predicts. Newton points out that they sought not to disprove coordinated stasis, but rather to gain a more sophisticated understanding of when it is applicable. Discovering more about the dynamics of these apparently stable Devonian communities is critical. She says such knowledge has immediate significance for marine community changes in our rapidly warming seas. Since geologist James Hall Jr. first published a series of volumes on the region's Devonian fossils and strata in the 1840s, the Hamilton Group has become a magnet for research scientists and amateur collectors alike. Okay. During Middle Devonian times, approximately 380 to 390 million years ago, the faunal composition of the region changed little over 4 to 6 million years. It's a significant amount for marine invertebrate communities to remain stable or locked. G. Brower and student researchers spent years examining 8 communities of animals that once dwelled in a warm, shallow sea on the northern rim of the Appalachian basin, which eons ago lay south of the equator. When the organisms died, sediment from the seafloor began covering their seashells and exoskeletons. Minerals from the sediment gradually seeped into their remains, causing them to fossilize. The process also preserved many of them in living position, conserving original shell materials at some sites. So the interesting thing there is the Appalachians were basically at the equator, during the Devonian. It's an interesting thought. And Appalachians were actually at one point the tallest mountains in the world, like what the Himalayas are now. That's what the Appalachians were during, I forget which geologic period that was. I want to say it was during the Paleozoic, though. These fossils currently populate exposed bedrock throughout central New York, ranging from soft, dark, deep water shell to hard, species rich shelf siltstone. It's like selling seashells on the seashore. Communities near the top at the bedrock exhibit more taxonomic and ecological diversity than those at the bottom. We can compare the community types and composition through time. They are remarkable sites. Coordinated stasis has been a source of contention since 1995 when it was introduced. At the center of the dispute are two model-based explanations: environmental tracking and ecological locking. Environmental tracking suggests that faunas follow their environment. Here, periods of relative stasis are flanked by coordinated extinctions or regional disappearances. When the environment changes, so do marine faunas. Ecological locking, in contrast, views marine faunas as tightly structured communities resistant to large-scale taxonomic change. Traditionally, this model has been used to describe the stability of lower Hamilton faunas. The Newton and her colleagues analyzed more than 80 sample sites, each containing 300 specimens. Special emphasis was placed on the Cardiff and Pecksport members, 2 rock formations in the Finger Lakes region that are part of the ancient Marcellus group, famed for its natural gas reserves. Good grief. We found that lower Hamilton faunas, with 2 exceptions, do not have clear counterparts among upper ones. Therefore, our quantitative tests do not support the ecological locking as an explanation for community stability in these faunas. Newton considers this project a final tribute to Newman, a professor of biology at the State University of New York at Cortland, who died in 2014, and Brower, who fell seriously ill while the manuscript was being finalized. Jim knew that he would likely not live to see this publication. That sucks. She says that this new work extends and in some ways completes the team's earlier research by further analyzing community structures in the Marcellus subgroup. It has the potential to change how scientists long-term view long-term stability and ecological communities. So obviously interesting. I love how you can tie plate tectonics to biology in this regard. Without geology, biology wouldn't have been where it was, and been able to fossilize where it did, without plate tectonics, without the geology. And that was an interesting read, trying to understand, it's some of it over my head a little bit, but pretty interesting that they're able to try and determine, why they are deposited in that way and how it explains an extinction event. they were pretty, what is it? They were stable for millions and millions of years. 4 to 6, I think, is what the article said. That's pretty interesting how it, well, they stayed around for a long time. They studied over 300 specimens. That's and just within the central New York area. That's pretty cool. Back. Oh, I skipped this one. So my son loves dinosaurs. And one of his favorite dinosaurs right now, because he has a toy, is the Spinosaurus. So I wanted to read this one. So new light is shed on the behavior of giant carnivorous dinosaur Spinosaurus. So a new research from Queen Mary University of London and the University of Maryland has reignited the debate around the behavior of the giant dinosaur Spinosaurus. And my introduction to Spinosaurus was for Jurassic Park 3. Funny enough, I didn't know it had actually existed, but apparently what Tyrannosaurus Rex was to North America, Spinosaurus was to Africa. And I remember learning that when I was playing the Jurassic Park video game on PS2, I think. All right, since its discovery in 1915, the biology and behavior of the enormous Spinosaurus has puzzled paleontologists worldwide. It was recently argued that the dinosaur was largely an aquatic predator, using its large tail to swim and actively pursue fish in the water. The new study, published today in Paleontologia Electronica, that's a badass name, challenges this recent review of Spinosaurus, suggesting that whilst it likely fed from the water, it may have swum, it wasn't well adapted to the life of an aquatic pursuit predator. Instead, it was like a giant, or giant, if flightless heron or stork, snatching at fish from the shoreline while also taking any other small available prey on land or in water. So, reviewing the evidence, the researchers compared the features of Spinosaurus with the skulls and skeletons of other dinosaurs and various living and extinct reptiles that lived on land, in the water, or did both. They found that whilst there were several pieces of evidence that contradicted the aquatic pursuit predator concept, none contradicted the wading heron-like model, and various lines of evidence actively supported it. So that's what I remember learning in historical geology about Spinosaurus, was that, what it showed in Jurassic Park 3, it was more of a fish eater. It wasn't chasing down Tyrannosaurus Rex and breaking its neck or anything. Dr. David Hone, senior lecturer at Queen Mary and lead author on the project, said the biology and ecology of Spinosaurus has been troubling paleontologists for decades. Some recent studies have suggested that it was actively chasing fish in water, but while they could swim, they would not have been fast or efficient enough to do this effectively. Our findings suggest that the wading idea is much better supported, even if it is less exciting. Okay. Spinosaurus was a bizarre animal, even by dinosaur standards, and unlike anything alive today, so trying to understand its ecology will always be difficult. We sought to use what evidence we have to best approximate its way of life, and what we found did not match the attributes one would expect in an aquatic pursuit predator in the manner of an otter, sea lion, or short-necked plesiosaur. One of the key pieces of evidence unearthed by the researchers related to the dinosaur's ability to swim. Spinosaurus was already shown to be less efficient swimmer than a crocodile, but also have fewer tail muscles than a crocodile, and due to its size, it would have had a lot more drag in the water. Crocodiles are excellent in water compared to land animals, but are not that specialized for aquatic life and are not able to actively chase after fish. Spinosaurus had fewer muscles on the tail, less efficiency, and more drag. Then it's hard to see how these dinosaurs could be chasing fish in a way that crocodiles cannot. We certainly add that the evidence points to Spinosaurus feeding partly, even mostly, in the water, probably more so than any other large dinosaur, but that is a different claim than it being a rapid swimmer chasing after aquatic prey. Though, as Dr. Hone concludes, while our study provides us with a clear picture of the ecology and behavior of Spinosaurus, there are still many outstanding questions. and details to examine for future study, and we must continue to review our ideas as we accumulate further evidence and data on these unique dinosaurs. This won't be the last word on the biology of these amazing animals. So, Spinosaurus was officially around, originally found in Egypt. Spinosaurus is thought to be one of the largest carnivorous dinosaurs to exist, probably reaching over 15 meters in length, which is about, what, 45 feet? The first known Spinosaurus fossils were destroyed by Allied bombing during World War II, which has hampered paleontologists' attempts to understand these unusual creatures. More recently, the dinosaur found fame in the 2001 film Jurassic Park 3, where it battles and defeats a Tyrannosaurus Rex. And that's the end of the article. Uh, yeah, and I remember watching that movie. I didn't know what the Spinosaurus was. So I remember reading more up on it. And then there was a video game that came out not too long after that. And yeah, that's how I understood Spinosaurus, was it pretty much just tried to fish. But according to this, it didn't really have the tail. It was like a crocodile. It didn't really have the tail to chase down a fish. So interesting. When my son is old enough, he'll love to know that, I'm sure. So this is a relatively short one. This one was posted by Penn State on January 26, 2021. Scientists identify flank instability at a volcano with history of collapse. So landslides caused by the collapse of unstable volcanoes are one of the major dangers of volcanic eruptions. A method to detect long-term movements of these mountains using satellite images could help identify previously overlooked instability of some volcanoes, according to Penn State scientists. Whenever there is a large volcanic eruption, there is a chance that if a flank of the volcano is unstable, there could be collapse. To better explore this hazard, we applied an increasingly popular and more sensitive time series method to look at all these movements or surface deformation over long periods of time. Using the time series techniques, the scientists found surface deformation related to flank motion had occurred at Pacaya, an active volcano in Guatemala from 2011 to 2013, when the volcano was largely quiet, and increased leading up to an eruption in 2014. Previous work had not identified flank motion during this time, the scientists said. The people have looked at the volcano with satellite remote sensing but did not detect this long-term flank motion or creep. Okay, because the surface deformation changes are pretty small per year, it can easily be below the detection limits of conventional methods, but still within the limits of Judith's work using a time series approach. Scientists track surface deformation using radar satellites sensitive enough to spot changes of just a few inches on the ground. Comparing two of these images using the INSAR technique creates an interferogram, essentially a map of surface movement, but the quality of the INSAR results decreases with the time separating two images and can be affected by even small changes like some vegetation growth or a buildup of ash spewed from a volcano. So this is remote sensing. Anyone that's interested in studying a volcano with remote sensing, this is your cup of tea right here. The team instead conducted an INSAR time series analysis using hundreds of satellite images taken over years and identifying surface deformation between the two, or between each, I should say. You can use many of these short-term surface movement maps to give you information of surface displacement over a long period of time. Then you look at the surface deformation maps and see how much each pixel has been moving since the date the first image was acquired. The results, published in the Journal of Volcanology and Geothermal Research, provide finer detail of volcanic flank motion and can reveal upticks in the rate that creep is occurring, like at Pacaya before the eruption in 2014. The kind of creep is not uncommon and not particularly dangerous on its own, but if you have extra forcings, like from magma being pressurized and pushing against the wall of the chamber or intrusion, it can trigger a catastrophic collapse. To be able to understand the behavior of the instability and potentially detect changes in rates of motion is very critical for monitoring that potential collapse. Pretty cool. I wonder if they're doing the same for Mount Crystal Ray. Localized. Mount St. Helens. The method shows promise for identifying deformation, particularly at volcanoes that lack expensive real-time monitoring networks and those located in tropical areas with thick vegetation that create problems for traditional INSAR. Blank instability is often studied at oceanic volcanoes where a collapse would trigger a deadly tsunami, but collapses also happen inland, including prominently at Mount St. Helens in 1980. Pacaya itself experienced a collapse sometime around 1,000 years ago, creating a debris avalanche that traveled more than 15 miles and leaving a prominent scar in the volcano. Wow. Subsequent eruptions have built the volcano back up and it could someday again collapse, the scientists said. More than 10,000 people live within about 3 miles of the volcano. If you take into consideration the last avalanche traveled 15 miles away, anyone living within the valleys around the volcano could be at risk. Wow. Okay. So this one was posted by the University of Southampton. Geological phenomenon widening the Atlantic Ocean. An upsurge of matter from beneath the Earth's crust could be pushing the continents of North and South America further apart from Europe and Africa. New research has found the plates attached to the Americas are moving apart from those attached to Europe and Africa by 4 centimeters per year. In between these continents lies the Mid-Atlantic Ridge, a site where new plates are formed, and a dividing line between plates moving to the west and those moving to the east. Beneath this ridge, material rises to replace the space left by the plates as they move apart. So, conventional wisdom is that the process is normally driven by distant gravity forces as denser parts of the plate sink back into the Earth. However, the driving force behind the separation of the Atlantic plates has remained a mystery because the Atlantic Ocean is not surrounded by dense, sinking plates. Now, a team of seismologists led by the University of Southampton have found evidence of an upwelling in the mantle, the material between the Earth's crust and its core, from depths of more than 600 kilometers beneath the mid-Atlantic ridge, which could be pushing the plates from below, causing the continents to move further apart. Upwellings beneath ridges are typically thought to originate from much shallower depths of around 60 kilometers. The findings published in the journal Nature provided a greater understanding of plate tectonics, which causes many natural disasters around the world, including earthquakes, tsunamis, and volcanic eruptions. So the team deployed 39 seismometers at the bottom of the Atlantic as part of the PI-LAB passive imaging of the lithosphere asthenosphere boundary experiment and Eurolab experiment to unearth the geological oceanic lithosphere astheno oh my goodness boundary. The data provides the first large-scale and high-resolution imaging of the mantle beneath the Mid-Atlantic Ridge. This is one of only a few experiments of this scale ever conducted in the oceans and allowed the team to image variations in the structure of the Earth's mantle near depths of 410 to 660 kilometers, depths that are associated with abrupt changes in mineral phases of, what is that called? Peridotite. There's multiple different types of the ultramafic peridotite, larzolite. I forget the other ones, but yeah, that's what they're talking about with mineral phases. The observed signal was indicative of a deep, sluggish, and unexpected upwelling from the deeper mantle. This was a memorable mission that took us a total of 10 weeks at sea in the middle of the Atlantic Ocean. The incredible results shed new light in our understanding of how the Earth's interior is connected with plate tectonics with observations not seen before. There is a growing distance between North America and Europe, and it is not driven by political or philosophical differences. It is caused by mantle convection. As well as helping scientists to develop better models and warning systems for natural disasters, plate tectonics also has an impact on sea levels and therefore affects climate change estimates over geologic timescales. This was completely unexpected. It has broad implications for the understanding of our Earth, or of our Earth's evolution and habitability. It also demonstrates how crucial it is to gather new data from the oceans. There is so much more to explore. The work is exciting in that it refutes long-held assumptions that mid-ocean ridges might play a passive role in plate tectonics. It suggests that in places such as the mid-Atlantic, forces at the ridge play an important role in driving newly formed plates apart, which I thought we knew already, but interesting. All right, so rocks show Mars once felt like Iceland. Crater study offers window on temperatures 3.5 billion years ago, and this is by Rice University. Once upon a time, seasons in Gale Crater probably felt something like Iceland, but nobody was there to bundle up more than 3 billion years ago. The ancient Martian crater is the focus of a study by Rice University scientists comparing data from the Curiosity rover to places on Earth where similar geologic formations have experienced weathering in different climates. So, Iceland's basaltic terrain and cool weather, with temperatures typically less than 38 degrees Fahrenheit, turn out to be the closest analog to ancient Mars. The study determined that temperature has the biggest impact on how rocks formed from sediment deposited by ancient Martian streams that were weathered by climate. The study by postdoctoral alumnus Michael Thorpe and Martian geologist Kirsten Seibach of Rice and geoscientist Joel Horowitz of State University of New York at Stony Brook set out to answer questions about the forces that affected sands and mud in the ancient lake bed. Data collected by Curiosity during its travels since landing on Mars in 2012 provide details about the chemical and physical states of the mudstones formed in an ancient lake. But the chemistry does not directly reveal the climate conditions when the sediment eroded upstream. For that, the researchers had to look for similar rocks and soils on Earth to find a correlation between the planets. So they took the data from well-known and varying conditions in Iceland, Idaho, and around the world to see which provided the best match for what the rover sees and senses in the crater that encompasses Mount Sharp. The crater once contained a lake, but the climate that allowed water to fill it is the subject of a long debate. Some argue that early Mars was warm and wet, and that rivers and lakes were commonly present. Others think it was cold and dry, and that glaciers and snow were more common. So sedimentary rocks in Gale Crater instead detail a climate that likely falls in between two scenarios. The ancient climate was likely frigid, but also appears to have supported liquid water for lakes in lakes for extended periods of time. The researchers were surprised that there was so little weathering of rocks on Mars after more than 3 billion years, such that the ancient Mars rocks were comparable to Icelandic sediments in a river and lake today. So on Earth, the sedimentary record does a fantastic job of maturing over time with the help of chemical weathering. However, on Mars, we see very young minerals in the mudstones that are older than any sedimentary rocks on Earth, suggesting weathering was limited. Oh, wow. The researchers directly studied sediments from Idaho and Iceland and compiled studies of similar basaltic sediments from a range of climates around the world, from Antarctica to Hawaii, to bracket the climate conditions they thought were possible on Mars when water was flowing into the Gale crater. Earth provided an excellent laboratory for us in this study where we could use a range of locations to see the effects of different climate variables on weathering, and average annual temperature had the strongest effect for the types of rocks in Gale crater. The range of climates on Earth allowed us to calibrate our thermometer for measuring the temperature on ancient Mars. The makeup of sand and mud in Iceland were the closest match to Mars, based on analysis via the Standard Chemical Index of Alteration, a basic geological tool used to infer past climate from chemical and physical weathering of a sample. As water flows through rocks to erode and weather them, it dissolves the most soluble chemical components of the minerals that forms the rocks. On Mars, we saw that only a small fraction of the elements that dissolved the fastest had been lost from the mud relative to volcanic rocks, even though the mud had the smallest grain size and is usually the most weathered. This really limits the average annual temperature on Mars when the lake was present, because if it were warmer, then more of those elements would have been flushed away, she said. So the results also indicated the climate shifted over time from Antarctic-like conditions to become more Icelandic, while fluvial processes continued to deposit sediments in the crater. This shift shows the technique can be used to track climate changes on ancient Mars. While the study focused on the lowest, most ancient part of the lake sediments Curiosity has explored, other studies have also indicated that Martian climate probably fluctuated and became drier with time. This study establishes one way to interpret that trend more quantitatively by comparison to climates and environments we all know on Earth today. Similar techniques could be used to perseverance to understand ancient climate around its landing site at Jezero crater. Parallel climate change, especially in Iceland, may shift the places on Earth best suited for understanding the past on both planets. So, it's pretty interesting that we can use, some elements on Earth to try and study and understand what's happening on Mars. It's kind of wild that sediments on Mars are older than any sedimentary rock we have here on Earth, but it makes sense because the weathering processes on Mars are not as active or not active at all as we have on Earth, because they haven't had flowing. Well, Mars hasn't had flowing water, in a long time. It sounds like billions of years at least. That's an interesting article. All right, so this is gonna be the last article I read on this episode. So, researchers trace geologic origins of Gulf of Mexico superbasin success, and this is from the University of Texas at Austin. So the summary is the Gulf of Mexico uh, holds update holds huge untapped offshore oil deposits that could help power the U.S. for decades. According to the researchers, the basin's vast oil and gas reserves are the result of a remarkable geologic past. Only a fraction of the oil has been extracted, and much remains buried beneath ancient salt layers, just recently illuminated by modern seismic imaging. Which is why salt tectonics right now is a big thing at the university I went to, UTEP. They do a lot of studies on salt tectonics. So it's definitely something, the oil and gas industry is definitely trying to understand. So the Gulf of Mexico holds huge untapped offshore oil deposits that could help power the U.S. for decades. The energy superbasin longevity, whose giant offshore fields have reliably supplied consumers with oil and gas since the 1960s, is the result of a remarkable geologic past, a story that began 200 million years ago among the fragments of Pangaea when a narrow, shallow seaway grew into an ocean basin, while around it mountains rose and then eroded away. The processes that shaped the basin also deposited the preserved vast reserves of oil and gas, of which only a fraction has been extracted. Much of the remaining oil lies buried beneath ancient salt layers, just recently illuminated by modern seismic imaging. That's the assessment of researchers at the University of Texas at Austin, who reviewed decades of geological research and current production figures in an effort to understand the secret behind the basin's success. Because of its geological history, the Gulf of Mexico remains one of the richest petroleum basins in the world. Despite 60 years of continuous exploration and development, the basin's ability to continue delivering new hydrocarbon reserves means it will remain a significant energy and economic resource for Texas and the nation for years to come, said lead author John Snedden, a senior research scientist at the University of Texas Institute for Geophysics. When we looked at the geologic elements that power a superbasin, its reservoirs, source rocks, seals, and traps, it turns out that in the Gulf of Mexico, many of those are pretty unique. The research was featured in December 2020 special volume of the American Association of Petroleum Geologists Bulletin focused on the world's super basins, a small number of prolific basins that supply the bulk of the world's oil and gas. According to the paper, the geologic elements that have made the Gulf of Mexico such a formidable petroleum source include a steady supply of fine and coarse grained sediment and salt, thick layers of it buried in the earth, marking a long time ago when much of the ancient sea in the basin evaporated. Geologically, salt is important because it can radically alter how petroleum basins evolve. Compared to other sedimentary rocks, it migrates easily through the earth, creating space for oil and gas to collect. It helps moderate heat and keeps hydrocarbon sources viable longer and deeper. And it is a tightly packed mineral that seals oil and gas in large columns, setting up giant fields. And hydrocarbon can be destroyed pretty easily if temperatures or pressures are too high, or if they're not high enough. There has to be a perfect balance between the two, so that's explaining why salts are important. The Gulf of Mexico has a thick salt canopy that blankets large portions of the basin and prevented us for many years from actually seeing what lies beneath. What has kept things progressing is industry's improved ability to see below the salt. According to the paper, the bulk of the northern offshore basin's potential remains in giant deepwater oil fields beneath the salt blanket. Although reaching them is expensive and enormously challenging, Snedden believes they represent the best future for fossil fuel energy. It's because the offshore, where many of the giant fields are located, offers industry a way of supplying the world's energy with fewer wells, which means less energy expended per barrel of oil produced. Snedden said there is still much to learn about hydrocarbons beneath the Gulf of Mexico, how they got there, and how they can be safely accessed. This is especially true in the southern Gulf of Mexico, which was closed to international exploration until 2014. One of the few publicly available data sets was a series of UTIG seismic surveys conducted in the 1970s. Now a wealth of prospects is emerging from new seismic imaging of the southern basin's deepwater region. When you look at recent U.S. oil and gas lease sales, Mexico's 5-year plan, and the relatively small carbon footprint of the offshore oil and gas industry, I think it's clear that offshore drilling has an important future in the Gulf of Mexico. Snedden research was conducted within UTIG for the Gulf Basin Depositional Synthesis Project, which he directs. The project has been continuously funded by an industry consortium since 1995. UTIG is a unit of the Jackson School of Geosciences at the University of Texas at Austin. And that was the last article that we're going to read today. Hopefully, I'll post one of these at least once a week. Next week's episode will be shorter since this was the first episode. I had a lot of material that I read and found interesting and wanted to kind of read through. Next week's episode will be much shorter. I hope you guys enjoyed this. Let me know if there's an article you want me to cover in next week's episode. Let me know in the comment section. Thank y'all for watching. Later, Essentials.